from 7:30. So we will have a break of 30 minutes between the first speaker and the second speaker. However, there will be a break of 5 minutes or so between the second and third speakers. And as for your information, we are experiencing bad weather at NIT Silchar today. Hope there is no technical issue during our session. So I hand over to Sakshi. Are you there?
Yes, sir.
Okay, so please start the session.
Good evening to one and all present here, and welcome on the third day of 1 week AICTE sponsored faculty development program on recent advances of NLP using deep learning techniques. Today, our first speaker is Dr. Pinky Roy from NIT Silchar, and she will be talking on speech recognition using deep learning techniques. Our second speaker is Tamar Solorio from University of Houston, USA. And our third speaker is Pinaki Bhaskar from SRIB Bangalore. Now, Dr. Pinky Roy is working in NIT Silchar for the past 17 years. She is actively involved in the research topics of speech recognition, healthcare, and machine learning. She has published several SCI Scopus journals, book chapters, and books. She has published papers in various top-level conferences of speech like TenCon and represented India in various international conferences in Sydney, London, and Singapore. Two students had already completed their PhD under her guidance, and they are now working in prestigious institutions. She is the recipient of Young Scientist Award, Rashtriya Gaurav Award, Distinguished Lady Alumni Award, and various other prestigious awards. She is the active member as guest editor of prestigious journals and reviewer, session chairs, general chair of the various conferences held in international levels. Now, may I request you, ma'am, to kindly start your keynote presentation.
Yes, thank you for such a very nice introduction. So today I will be just a minute. I'll just first share my screen and then we'll start the presentation.
Okay, please.
Yeah. Yes, can you see my screen?
Yes, yes.
Yes, okay.
Yes, ma'am.
Yeah.
Please.
Yeah, thank you. So today I will be giving you a brief presentation on how we can do the speech recognition using the various deep learning techniques. So to start with, so in my today's lecture, I will be covering these points like introduction to the speech processing, various applications of speech. And in between, I want to say that if you don't hear my voice or any technical issues are there, please inform me. Okay, so then introduction to audiovisual automatic speech recognition. It is a part of the speech processing. And audiovisual feature-based multimodal authentication. Then we will, I will give you some introduction that what is the language identification and how we can apply different deep learning architectures in for Indian language identification. Okay, to start with, the first question is that what is a speech? like what is, you can say, communication. So what is actually the electrical communication, or you can say it is a speech processing. So what do you mean by communication? Communication, usually it means we are exchanging the information between ourselves. Speech is a medium through which we exchange the information. Suppose I am talking to you, so I am using my speech to convey you the information that I am trying to share with you in a particular language. Suppose I am talking with you in an English language. So in the speech processing, there are different extracting. We have to extract the speech information, and then we have to model the speech in the case of a machine. So, and what are the things actually we require for processing of the speech? The main things that we require is that first we need to know what is the message that a person is trying to give, and then we should know what language the person is trying to use. This happens in our case also. What is the language that person, we should know or understand that language. So if some person talks to me in Tamil or German, I will not understand because I don't know that language. So in the case of machine also, the message, the language should be known, the speaker who is speaking, and then the gender is also required, and the emotions. Okay, these things we can use it. So what is the difference between the speech processing between the human and computing machine? Okay, so in the case of our human being, we can easily learn a speech. Okay, so but in the case of a computing machine like a computer, so we are, the machine, what does it do? It tries to depict the activities of the speech, and then it tries to find out the pattern, what is the pattern of the speech, and then it tries to apply the various machine learning techniques for recognition of the speech. So computing machines or the computer, we can also apply the deep learning techniques, which is we can say it is an improved version of a machine learning. It is in more, it gives us more accurate way of processing of the speech. So this is a simple communication. Here there is a one person, he is the talker who is talking, and this is the person who is listening. So you can say that I am the talker here, I am generating the speech, and you people who are listening to me, you all are trying to recognize the speech or trying to understand that what I am trying to convey you through this lecture. So in this, when the speech is generated, first of all, in our brain, we first formulate the message, that what is the message I want to give to the another person. Then we try to find out the language code, that what language I'm going to use. It's English, Hindi, Bengali, what I'm going to use. And then after that, there are neuromuscular actions, which depends upon like the various nerves that are present in our brain, the eyes and all those things. And then there are the talker will generate the message. How it generates? Based on the vocal cords and the acoustic system. It tries to generate the message. And from the vocal cord, the message is generated, and then finally through the acoustic wave, the whatever the thing I am saying to you, it goes to your ear. So in this ear, there is a basilar membrane motion, which does all the processing of the speech, and then there is a neural transduction. Like that means it is trying to extract what I am trying to say, and then there is a language code. Then it will depict that in what language code the person is trying to give the message. And finally, the message comprehension. Message comprehension means depicting the meaning of the message, which is also known as semantics. So this is the part of speech recognition in the part of the listener, and this is the part of speech generation in the context to a talker. So when we talk about the speech, there are two types of communication. One is your verbal communication, verbal communication, another one is your non-verbal communication. So verbal communication is always oral. Whatever I am speaking to you, it's a verbal communication. It's a spoken language. And non-coughing, like these are different kinds of non-verbal communication that we usually do, blinking eyes, then making faces. So these are different kinds of non-verbal communication. But there is a signal. You can say these are kind of signals that we are giving. And this is a non-oral, where we are not speaking, but we are writing it. Whenever we write something, that is also a kind of communication, or sign language that we use for different dumb people, or sometimes to show the directions also we use the sign language, and the different gestures of our body language, etc. So these are different kinds of non-verbal communication, and these are kind of verbal communication. So this is an example of your lip production mechanism, speech production mechanism. So these are our lungs and trachea, through which the air is pumped, and because of the pumping of the air, the speech comes out from this portion. Okay, so there are in this portion we have tongues, lips, teeth, nostril, nasal cavity, everything. So all this, all the part of the mouth, it plays a very big role for processing of the speech and finding out, for producing the speech. Neck, epiloglottis, these are the small biological parts of our system. So all these things play together for creating the sound that we are when we talk. So the vocal folds, sometimes it constricts, so it is opening and it is closing, so that we can hear to the voice. So now this is my biological system. Now how we are using or converting this one into the mechanical system, or into the computer, so that computer can also produce or understand the speech as we human beings can do. So modulation of the carrier. So we measure the frequency of how that person is producing the voice, and these are some of the fundamental frequencies that are there, and air flows from this portion, and then this speech signal is produced here. So there are two types of sound when we talk. So whenever I'm talking to you, suppose I say I am fine, so there is a gap. I, then I say am, and then I say fine. So this gap is known as your unvoiced, which is required, because we don't talk at a stress, we always put a gap. So these are all unvoiced, okay, where the signal fluctuation will be very low. And when I say I, and then I take a pause of 2 seconds and say I am, then fine. So this 2 seconds pause there, the signal variation will be very low. So now we can see this is your human speech communication chain. So this is the speech chain. This is my speaker, and this is our listener. And how the speaker, these are your different portions. So this is the brain, and the brain is trying to find out the signals, what is being taught, what things are being told. And here, this is again the same thing, the connection of ear with the brain. And this is the person's mouth. Here are the vocal muscles that are present in our neck. In this place, we have those sound waves. And these are the motor nerves, which helps to produce the sound, that sound waves it tries to produce. So here you can see that these vocal muscles, together they come up, and these sound waves are produced here. So this we have to now convert it into the computer term, so that our computer is now able to understand the human speech communication process. So this is the linguistic level. Then we have the psychological level, then acoustic level, then physiological level, and then again we have the linguistic level. So we'll see in details after this. Okay, so the first thing is that why we require that our computer should understand the speech. Why it is required? Why I want my computer to understand what I am talking. Engineers, they used to dream of creating some computing machines. Speaker means I am Ram, or I am Sham, or I am Dr. Pinky Roy. So this, my computer will try to find out that who am I. And this trial was trying to be done for, you can say, decades back. People are trying to do this. The scientists are trying to do this. The reason for this is that, you see, whenever we use a computer nowadays, it's a very hectic process to use a computer because we have this spondylitis pain and so many things we are having. Through which the only input we can give to a computer is by typing. We need a keyboard, we need a mouse. If I want to interact with the computer, we need to type each and everything. So it's actually the this COVID situation, and the day by day we are depending on the online modes and everything. So we have to spend a lot of time in the computer, and if we start like typing and all those things we keep on doing, so it is having a lot of health hazards. So from the past few decades, the scientists and engineers are trying that why not, instead of typing, if the computer, my computer is able to understand what I am talking, instead of typing my thesis, if I talk, if I say the words and computer understand and it types everything, then it will be easier for me. So that is known as speech to text, and it is now almost, it is used many places. We are using this speech to text. So that's why there was now in the Google also we have this search techniques in which now my typing and everything, but he knows that if it will search it, so they talk to the computer, they use the maximum use of this Google voice search engines. So like that, small applications are now coming up, and now there is a lot of emphasis on making this our devices, this mouse and you can say a keyboard free. Maybe after 20 years, there maybe the machines will come up where there will be no keyboard, no mouse, nothing, and we can directly talk to the computer and our work will be much easier to it. So when we say about speech recognition, then there in our in the world there are around 6,800 languages spoken around the world. So it will always be comfortable if the computer understands not only English but whatever the local languages we are speaking, so that it is not like that the computer will be accessible to only the learned people. Nowadays, the computer's data is accessible only to the people who are learned, who knows a lot of, they're having a lot of degrees and all. But what about the farmers? What about the people who are working in the other sectors? Maybe they don't have much education, but lot of information for the common people are also stored in the computer. So if the computer is able to understand all the local languages, Bengali, English, Hindi language, Assamese, so many languages we have, Tamil, Telugu, everything, all the languages when the system will understand, then the computer will be a very easy thing which will be accessible, data and the information will be accessible to all the literate and the illiterate people. That's why there is now a lot of stress on understanding the language identification. That's why our next phase, we will talk about this, how to do the language identification. So this is actually the main motive for why we are now, there is a lot of stress on working on speech recognition or speech processing. So, but when, as I'm telling you, if you imagine, it's a very fancy kind of thing. We feel very good to imagine that kind of thing. But actually, whenever we try to implement this into a computer, it's very hard. So it's proven to be hard due to the cognitive nature. It's very hard technique. It's not so easy to make a system understand our speech. But still, the trial is going on. So even the big companies like Google Speech, IBM Watson, Apple Siri, Amazon Alexa, these are the different types of things that are small application type of things which are coming out as a part of your speech recognition. So now little bit people are becoming, you can say 10% people are becoming commercially successful. These companies are becoming, and because of that, this kind of devices are now coming up. So there is a lot of interest in the speech processing area, and there is a lot of scope if anyone wants to work in this area. There is a lot of scope, you can work in this area, and the commercial success of speech processing is now mainly it is now towards the deep learning, because deep learning, it's a very new technique which is now coming up. And if you want that speech processing should be successful in the commercial level, then we should know the different deep learning techniques that we can contribute to it. So, but the deep learning technique, it is having some of its limitations, like we require very good infrastructure, like big GPU and the huge heap of digital data for processing. So these things are required for processing of the data. So as I've told you, so this part is very clear to us. So speech is what we are trying to communicate. So it may be in the words, digits, phrase, anything it may be. Digits also. So whenever we talk anything, this kind of signals are produced by our system. So these are, as I've told you, some applications. Here it is again pointed out, some speech applications. Here the speech signal is there, and then you can see this is your speech recognition. Speaker recognition is one application. Language identification, as I've told you. Emotion recognition is also one of the application. So speech recognition is actually to understand in a given speech what are the meaningful words and what is their importance. Okay, speech recognition handles only that part. And because whenever a line is spoken, so always it is taken care of that which are the important things which should be taken care of, and which are the things which should be neglected. So speech recognition mainly handles that part. Speaker recognition, as I've already told you, that recognizing the speaker, who is the person actually speaking. Suppose the Barun is speaking or Pinky Roy is speaking, who is the person who is actually speaking. To understanding, finding out, recognizing the speaker. And this is a very important part, as I've told you, identification of language or language identification, that which language the person is speaking, whether it is English, Hindi, whatever language. So language identification handles that part. Language, it only identifies the language. And then the emotion recognition. Emotions, it's a very important field nowadays. People are working on it. Through this emotion recognition, many of the medical things can be solved. And whether the person is feeling joy, he is in the stress, or he is angry. So many kind of emotions can be found out through the speech. So it is this emotion recognition is having used in the healthcare apps. Nowadays, you might be knowing that a lot of work is going on in the healthcare field. So emotion recognition can be easily used in lot of healthcare recognition apps. So this is the framework, and this is the paper from which it is taken. So you see here, this is the main one. We want to convert the human machine speech communication. So what it is actually, I am talking to a machine and machine is understanding my speech. So this is the whole part, half of this, and then here it is speech coding and transmission. So speech needed to be coded properly and transmitted. So you see, this is again divided into two parts: speech coding, speech decoding. Here it is spoken language identification. Whenever we try to communicate with the machine, we first the machine should try to understand the language. And then another part is your spoken language generation. Generation is also important part, which is done by a speaker, and understanding is done by a listener. Then we have speech recognition part, compression, cognition. Then under this comes your text to speech. So it is very common. You might have seen, like now in the Kindle and all, whenever we try to read any book, if we give text to speech, it automatically it reads for us. Any text, any book, it reads for us. So that is your text to speech. So it comes under this. Then after that we have this perceptions, then production of speech, then synthesis, then analysis of this speech waves. So this is the way actually how our speech signal processing framework works. So here I'm just going to one of the applications, so that you will find a little bit interesting to know about the speech. So this is a work one of my student, Dr. Shashwati Devna, she has done, and this work was also got a lot of appreciation also for this work. So in this work, what we have done is that here, whatever the speech the person is talking, audio speech, that audio speech was combined with the, just a minute, huh? Yes. I'll take just a 2 minutes break.
Okay. Okay, ma'am.
Yes. Can you see the slides?
Yes.
Yes. So here, what we have done is that whatever the data, that speech data that we get, that was combined with the video data. So the reason for that was in our practical experiments that we have gone through for various papers and all, we have seen that whenever we go for speech recognition, the speech, it never gives you 100% recognition rate. The problem with the speech recognition is that whenever the speech is recorded, you may try with the Google voice search also. You can take the mobile in different places and you can test the system. That whenever there is a voice or there are noisy environment you are there, the system will not be able to catch the whatever the speech data you are saying properly. It types wrongly. You may try this one. It types wrongly. It's not able to recognize properly. So the problem with the speech recognition is that if there are noise and other factors are there, so sometimes it is not able to recognize properly the speech. So or maybe if you are but in the case of whenever we do some practical applications of speech, if it is not 100% accurate, we cannot use it. We can use it for Google voice search, we can use it for Alexa, we can use it for any other systems. But if I want to use speech recognition for authentication purpose, I can't use speech recognition because it never gives me 100% accuracy. If I say that I am locking my mobile with my voice message 1234, I am giving the password of my mobile as 1234, and 5 times it is not recognizing and 5 times it is recognizing, then you can understand that what will be the situation. You will throw away your mobile. That is not working. So because if it is not working, what will happen? The lock will not open. Now we use fingerprint and all those things, so lock will not open. So that's why the speech is used for various things, but not for the sensitive applications. If you say that if I want to put a password to my voice password to my mobile, so that I can't put, because 90% maybe it will give you correct result, but sometimes it is there, it will give you bad results. So if you are supposed in a train, it is having a huge noise outside and you're trying to open your mobile, it may not work properly. So that's why the speech is not used mainly in the sensitive applications. But the advantages of the speech is that it is very secure. Like if my system is trained with my voice, any other person cannot come and open the computer or the mobile with his voice. Or suppose people say that if I do mimicry, then what will happen? No, mimicry also it will be able to catch, because every person's vocal track is different. So as you might be knowing that iris recognition of the eye, it is very authenticated, because every human being's that eyeball or iris, it is different. So same way in the speech also, every person's vocal track, the vocal track design is very, very unique. So because of that, if I know your password also, if I go and try with 1234, it will not open. So that's why speech recognition is very secure, but the problem is that we cannot use speech recognition in the sensitive applications. So because of that, we thought that why don't we try for a bimodal. So we have went for a bimodal in her PhD work, in the Shashwati's PhD work, where we have combined the speech of the person as well as the video of the person. So what it actually means is that suppose I am using this whole one for some authentication purpose. So, and here what we have not taken the very big line or something like that. We have taken small digits like 1, 2, 3, 4. So maybe it will work in the ATM pin, or it may work in the mobile phones as for authentication, or it may work in my laptop as my password. So like that we have thought, and we have taken only digit identification. Here it is only doing digits. So here the audio, suppose I am speaking, so my voice is recorded here, 1, 2, 3, 4, and then my video, whatever I am trying to say, that is recorded in this place. Okay, so this is recorded in this place. So in this case, you can see speech recognition from the audio and the recognition of visual speech. These two are combined. Speech and video is combined. And then we have made a model whose name is audiovisual speech recognition. Okay, so here it is. Here it is. Audio-visual fusion is done here, that we have done by ourselves. Fusion was done, and then finally we have recognized the audio-visual speech. So here, what we have done, how we have done is that we have collected the audio-visual data in the lab. She has recorded with a camera. She has recorded the data of some people, recordings 1, 2, 3, 4, along with the not only the speech, along with the video and the audio, both were recorded together, audio, video, but there were very small clippings. Okay, because in the case of speech, if you take very long sentences, it may have difficulty in finding out. So it is very small fragments. It is 1, 2, 3, 4. It hardly takes half seconds or something like that to record it. Then after collecting the audiovisual data, audio feature extraction is done. Then visual feature extraction is done. And then then the audiovisual speech is recognized. And finally, we do the fusion of both the techniques. So here we can see is that you see this is like how this approach will help us. If here suppose a person is there is a mobile, or there is a computer, or there is whatever the devices the person is using, so it may help in finding out in authenticating the person, or it may be ATM machine. So it will help the person to do the process of the authentication. So how it does, there is a cloud somewhere it is present, virtual machine, cloud manager is there, and here it is doing the multimedia authentication server. So we can imagine, suppose there is an ATM machine, I don't have my ATM pin, I don't have to remember my pin. If someone steals my pin, then my money will all go out. If someone uses my pin in the credit card, in the net, my money will go out. So these kind of issues will not be there, because if this if you are able to come up with audiovisual recognition, so during that time there will be just a camera will be there, and there we will go and we will just tell the numbers 1, 2, 3, 4, and because my face it is recognizing, along with that my voice also it is recognizing. So once it is recognizing my voice and the face, it will give access to the whatever money I want to draw, or if suppose I'm using a laptop, I want to enter to a laptop. So it will be a very safe kind of communication. So that's why it will be very difficult for the intruder to spoof the multiple modulators. So nowadays there are so many problems, like people are calling the senior citizen aged people, and they are saying that give your OTP. So people are taking the OTP, and it's very easy to crack. So but if this kind of system comes into picture, face-based authentication system, so this kind of problems we will not handle in future. But there are some of the issues that we have gone through when we have worked in this audiovisual part. Actually, this is a very new field, and very less work is done in this field. We have tried to do our contribution to this field, and very less work is done. And Shashwati has already passed out. One more student has come, so she will be continuing this work. So in this work, the problem is that whenever the system is trying to identify the face, if there are the lighting variations are there, it may not recognize the face properly. Like suppose the light is the light is too high, or light is very less, or it is very dark. So during that time, it is having problems. Or suppose specs, I am wearing the spectacles. So if a person is wearing the spectacles, so during that time also it cannot recognize properly, because whenever it does the face recognition, it tries to find out the shape of the eyes, shape of the nose, lips, then the position of the cheeks, like that. So if we are wearing a specs, then how it will try to find out the eyes? So it cannot find the eyes, and during that time this visual recognition faces some problem. So there are some these are some of the limitations we can say that we faced during that part. But the best part of it is that if due to the noise or other factors, the speech, my password is suppose 1, 2, 3, 4, the system is not able to identify what I am trying to say, 1, 2, 3, 4. But if it sees my face in the video and it can identify me with the visual feature recognition part, then it will give me the access. Okay, that is the best part. So we can, if we can use this kind of model for authentication purpose, because if suppose due to some reason my face is not recognizing properly, then the speech will work. If the speech is not recognizing properly, then face will work. So based on that, this model was designed. So as I've told you, so these are some of the applications where we can apply. So audiovisual, it can be used for web browsing. It can be used in the air traffic control rooms. We can use it for hands-free computing also at the advanced thing of it. And then it provides the security. As I've told you, it will play a very good role for giving security of an application, of the smartphone and many of the things. So many of the payment gateways such as PhonePe, Google Pay and Paytm, all these things, they can also use the authentication purpose. And then we have the voice dialing. There also it can help the disabled people for communication. And we have the speech-based communication, which is known as medical documentation. There also this audiovisual speech recognition can help a lot. But there are a lot of limitations of this one that we will handle. We have to handle if you want to work with it. So can we take 5 minutes break and then we will start again?
Oh, yes, please.
Okay. Okay. We'll go for 5 minutes break and then again we'll start.
Okay.
Yes, welcome back. Yeah, shall we start?
Yes, please.
Yes, ma'am.
Yes, okay. So these are some of the applications of audiovisual automatic speech recognition. So this is, you can say, this is a research topic of speech recognition, and it is having a very wide scope if anyone works in this area, because this is a very new field, combining audio and the video, and it is a little difficult also. So some limitations are there, and the people are trying, the scientists, engineers are trying to work in this area. So if anyone wants to work in this area, he can work in this portion. So this is some of the interdisciplinary nature of speech technology. So the speech, it is not limited to our computer people. Here the speech, it is a very open field where the computer linguistics role is also there, where we have neurolinguistics people, they can also have a big role. Psycholinguistics peoples are there. So it is a combination of engineering, psychology, linguistic, artificial intelligence. So all these people can come together and make the speech work in a very good manner. If you want the link in this paper, it is given that how these people can work together to make the speech a better recognition of speech technology in the better way. Because when we try to recognize the speech, we need to understand the engineering people will only put the data and they will use some algorithm and try to do the things. But the linguistic people, they know how to compute the data and how to find out the important information from the speech. So all these people can have a very good role in making the speech technology a very successful part. So if anyone wants to have details of it, you can see in this paper, which is the link is given in the below. Another part of the speech recognition is language identification. So during my PhD, I have worked on the language identification part, and one of my students is there. He's also working in this field. So as I've told you, language identification, it is a very important field of speech. And because, as I've told you, that we don't want our computers to understand only English. We want that our computers should understand any language. It may be German for foreigners. For India, we want that it should recognize all the languages which are given in the Constitution of India. 17 or 21 languages it is given. We at least want that in India it should understand all the languages. So if it understands, that computers will be very easier for us to use. We can speak in Bengali, computer will understand. We can speak in Telugu, Tamil, computer will understand. So that's why this field is also having a very wide scope if anyone wants to work in this area. So here what we're trying to do is that the main task is to just identify the language spoken by a speaker in a given utterance. Whatever the person is speaking, it will try to identify the language. So why do we need, and what are the applications of language identification? Suppose I am talking to a call center. In the call center, always it is given option. You talk either in English or in Hindi. We have two options only. But if this kind of in between and machine is there, which will identify the language. Suppose I am talking and it is identifying that I am speaking in Bengali. So it will automatically route the call to the operator who is there at the remotely, and he can access all my problems in Bengali language. Or it recognizes that I am speaking in, suppose, Marathi. So it is recognizing the Marathi language, and then it can route the call to the Marathi speakers. So in that time, this work will be reduced. And the security applications to narrow the search space. So it can also help us in the security applications also. So multilingual information retrieval, it can be used. Hello. Yes.
Ma'am, how it will help in the security?
Security, you see, there are, yes. Security, there are a lot of applications of this one. As if I tell you, some applications are there. This when the two people are talking, suppose the India is talking with US, the secret agency of India is talking with the secret agency of USA, then they don't use the simple English language or simple Hindi, whatever the language they don't use while talking, or there is a code language they actually use. Okay, so they usually use the code language, and as we use in the encryption decryption, the same way the person who is there in the USA, he knows how to decrypt that language. Okay, so he knows how to decrypt the language, and then he will decrypt the language and he will try to understand what is speaking. So in between, if some person, suppose from Pakistan, some people are trying to know that what India and USA, they are talking with each other, security agencies, what they are talking with each other, so they will not understand. Okay, so these kind of many applications are there like this. And when I have, very interestingly, when I completed my PhD work and still my students are working, I get several mails from, I got mail from China, I got mail from Pakistan to give my codes because they want to depict. Maybe there is some secret agency, they are constantly mailing me that they want my codes or to explain them how it works. So it is actually behind our, beyond our scope. We should not do all this thing. From China also, I got many mails like how we are doing this work to explain it to them. Okay, so it is having a very wide range of applications, this language identification.
Okay.
So, okay, so multilingual, okay, it can be used in a hotel lobby or international airport. Okay, so whenever we go to a very big 5-star hotel or international airport, the problem is that many people are there who don't understand English. Chinese are there, they are not proficient in English. German people, France people, they are not proficient in English. So if, or suppose we are going in a international airport, every person does not know English. So if there is a multilingual information retrieval, suppose the system is there, the person is, it is trying to identify the language. So it has understood that person can understand Telugu language. So whatever the information that will be given to the person, he will get all the information in Telugu, or he will get all information in Hindi, German, whatever, France, any language. Okay, so if this kind of system is developed, then in international airport, people will face less problems. So information, it can be used in the information query system. Suppose I am asking some questions, and I don't know the language, I don't know the English, so I can communicate in any language and I will get the answer. Then the spoken dialogue system, spoken document retrieval. Spoken document retrieval, its very common example is the Google voice search. In the Google voice search, I am suppose speaking in Bengali, so it should understand my language, and then it will help me in finding out that document in Bengali. So how I will retrieve the document in a particular language. So multi-language speech recognition, many applications are there of language identification, and it's totally open topic. Wide research can be done in this area. So here I am just talking about some technical terms that we use in the spoken language identification. This is my speech. This is the raw speech. Whenever we talk, the speech comes something like this. There are various softwares are available which will help you to find the spectrograms of the speech. So this is the way. This is the word that is being spoken. The word is, my name is Ravi Kumar, and this is the basic sound unit. Okay, this is how actually in the system the things are working. So there are different ways in which we can do the language identification. One is your implicit LID system and explicit LID system. So in the implicit, we will just put the speech signal, and after the output of the system will be identification of language. And here in the explicit one, first the speech signal will be identified using the speech recognition system, and these phonemes or the words will be given to the LID system, and finally the language will be identified. So here phonetic based, morphological based, static based.
So can we say that just
Yes.
the explicit system is an extension of the implicit? Nothing more than that?
No, these are two different kinds of model. These are two different kinds of model. Two different kinds. Okay, so in the
but
implicit one,
it is looking that just one more step is there only. We are adding fonts or words in between the speech recognition system.
no. It is there, but the models are different. Okay, it is there. One more model we are adding, but the more you can see here, the models are different. Here it is acoustic based and prosodic based approach. But I will explain you in the other slides. I will explain you. Yes. Any question?
No more.
Okay. So, but in the explicit LID system, what is there is that here it is phonetic based, morphological based, and syntactic based. As we study, in the compiler design, we have different parts: syntax, semantic. This part. In the same way, in the same way, in the language identification also, it is divided into different parts. We break the words. The words are there. We break it into different parts, and then we try to find out the meaning. This is the little different part, explicit way. And implicit, there is a language identification model in between, and we will actually study this implicit part. Explicit word part is a little bit tough for us because explicit part is handled mainly by the linguistic people, because they know how to break a word. Suppose this is various. Suppose this is written various. So it will be divided into 1, 2, 3, 4, 5, 6, 7 parts. And then it will try to find out.
Can we say that the implicit system is just like signal processing? It's like that?
I think you listen first. You listen first, then you can ask questions. Okay, you listen properly. I think you will get your answers. Okay. So in the explicit part, it will be divided into different parts, and then the linguistic, he will try to find out the meaning, and then finally the system will be recognized. But here in the implicit part, what is done is that the acoustic based, it is acoustic based, and the prosodic based approach. These are some algorithms are there which will apply. So here you can see. Okay, so these are the sequence of input features which are mapped to one particular language. So this is the speech from language 1, language 2, language L, different. These are the training phases. And then how it is actually done, how we find out that which language it is. Suppose the speech is there from language 1 is English, language 2, suppose German, language L, suppose France, China, something is there. So what is done? First, we will extract the speech parameters. We'll try to first find out the parameters of the speech of each of the language. Okay, and then we will try to model the parameter for language 1, language 2, language L. We will try to model all the speech. After the modeling is done, then speech of the unknown language. After that, we will do the testing part. Okay, then in the testing part, what we will do, any speech. Suppose I have given 3 languages, German, France, and Chinese, and out of this now I am testing with the German speech. So in the German, the features will be extracted here, feature parameters will be extracted here, and finally it will try to find out the likelihood that which language it is, it may be falling into, because here these parameters are there, no, lambda 1, lambda 2, lambda L. So it will try to find out the maximum likelihood that whether it is a German, it is closer to a German language, closer to France, or closer to Chinese. So since it is closer to German, so finally it will find out that this is my identified language. So this is a simple way of how we are trying to do the language identification. But if you want actually to do work in it, so it's a big process. So you will have to go through the papers and all those things for working into it. So here comes the answer to the question that you are asking to me. Distinctive features of spoken language. You see here, as you are asking me, what is implicit and what is explicit part. So here you see, this is the implicit. In the implicit, we use acoustic-based and prosodic-based approach. So this is your acoustic and prosodic. So whenever the speech is given as input to the system, then there is the words are broken into, as I've told, lexical different words, and then prosodic things are applied. What is prosodic? Here the duration of the speech is taken care of. What is the pitch of the speech? Pitch means the graph level high. The pitch of the female voice is always higher than the male voice. Then the stress level included. These things are calculated in your prosodic one. And then in the phonetic n-gram LM, this is one technique which is used. And in the acoustic part, the features of the speech are extracted. So how it is extracted? There are different techniques for extracting the features of the speech. Like MFCC, it is known as male frequency substral coefficient. One approach is there for speech for extracting features. Then PLP, then SDC, shifted data substrum. So delta substrum. So these are different kinds of feature extraction techniques which are used to find out the important features of the speech. So we usually use this approach. This is known as your implicit LID approach for identification, because for computer engineers, we are limited to this part. This part is little tough because here, phonemes word, here we require linguistic to work on it. So linguistic, there are proper linguistics are there who work on this field. So here, here you can see after that. Okay. So your question is clear. Your answer to your question is clear.
Yes, ma'am. Yes, ma'am.
Who was asking? Is it clear?
Yeah.
Okay. So different features and modeling techniques for language identification. Now we have different features, techniques, and modeling for identifying the language. So this is the low level to this is the high level, and MFCC, LPCC, these are the different ways for extracting the features. Then prosodic features are actually the pitch. What is the pitch of the signal, the high duration when the signal is something like this? What is the pitch of the voice? Energy, then duration of the speech that is recorded. And then lexical and morphological features where we have word units, grammar, everything which comes into the picture. So in this we have three different, these are modeling. Okay, once we extract the features, these are my features, we extract the features. Features extraction actually means finding out the important parts of a speech. Finding out the important features of a speech, sorry. So after finding out the important features of the speech, then we do the modeling. So in that modeling, here comes our all those machine learning techniques we have heard or we have learned. Here everything comes. Support vector machine, you might have heard about it, SVM. It's a very common technique. Gaussian mixture model we can use. These are all parametric. SVM is a non-parametric model. And under parametric model, we have GMM, commonly known as Gaussian mixture model, GMM, probabilistic linear discriminant analysis, which is known as PLDA, then joint factor analysis, I vector. These are the different parametric model. And different ANN models that we can use is that autoencoder, deep neural network, DNN, that we will be studying today, and then restricted Boltzmann machine. These are different kinds of ANN models that we can use. So these in the backend modeling, these are the different kinds of machine learning approaches we can use here. And these are the different ways we will extract the features. After extracting the features, there is, you can just imagine there is a model. We are just putting the extracting features into that model, and it depends upon us that which model we will be selecting. It depends upon your application. So as I've told you, LPC, it is a feature extraction technique, how we are going to extract the features. So I'm not going much into details of it, because it's if you want to try to implement something, if you go to the MATLAB, it's totally given LPC. So these are the different parts of your LPC. It will take the speech signal, then frame blocking will be done, windowing, autocorrelation analysis, LPC analysis, and finally the LPC will be given as output after that. So as computer engineers, we don't mainly work on the feature extraction technique, because here a lot of signal processing comes into picture. So we can't do much changes here. So we use the technique as it is. Suppose we have this MFCC. So LPC is an older technique which is not used nowadays much, but MFCC is a new technique which we use. So in the case of MFCC, what is done, it is a very new technique that we nowadays MFCC is mostly used for recognition. So in the case of MFCC also, we have, these are the different parts: preemphasis, FFT, ML, scale, log, discrete, cosine, transform, MCC. These are different parts of MFCC, how we are doing. So SDC is another technique, PLP is another technique. So these are different kinds of techniques we are using. As I told you, LTC is one technique. So yeah, SDC is another one. So here what is the thing is that here we can't do any changes, because these are all, you see here, these are all filtering techniques, filter, analysis, log, because here all the part of signal processing comes into picture. So if any person who is working in the signal processing area, they can try to do some changes into the feature extraction technique. Since we as a computer engineer, we usually work on the algorithm part, so we try to do here we use the model whatever we want. LPC also you can use, MFCC also you can use, SDC also you can use. But the main changes we try to do in this kind of techniques. Okay, so these are the different modeling techniques that we use. That, as I've told you, this one. Modeling techniques. These are the different kinds of modeling techniques where we try to do some changes or we use some different models and try to see what kind of result it is giving. So, okay. There are again two different kinds of feature extraction techniques, which is known as your deep bottleneck features. So here in this deep bottleneck feature, it's a part of your deep neural network, and here we can, what we can do is that we can lower the dimensionality of a particular hidden layer where the number of neurons are very less. If you want, we can lower the dimensionality of a particular layer. So this is known as deep bottleneck features, which we can use in the case of ANN. And another one is there, which is known as deep features from convolution neural network. So here also, in the case of convolution neural network, we can do some changes in this part. So now coming to the deep learning. So what is actually a deep learning? So it enables the computers to perform the intelligent task. And as we know, pattern recognition, it is recognizing the patterns from a given data. And after that, our main you can say father is artificial intelligence, son is pattern recognition, the son of pattern recognition is machine learning, and machine learning son is your deep learning. So this is, you can say, superset, subset, and this is a very small subset. So pattern recognition is a part of AI. Machine recognition It's also a part of AI as well as pattern recognition, as we know what is machine learning. And deep learning, it is a part of AI, pattern recognition, machine learning. Means if you want to know about deep learning, you need to have a very good knowledge of AI, pattern recognition, and machine learning. Then the understanding of deep learning will be very easier to you. So here it tries to learn the underlying patterns in the given set of raw data. So without being explicitly programmed. So it is how we are going to do the deep learning. I will explain in much details. So how the deep learning came into picture? It came from the neural networks. Deep learning, it is totally a part of your neural network. So the neural network is a simple network, as we know, is a set of inputs, outputs. In between we have set of hidden layers. So in the neural network, deep neural network example is your feed-forward neural network. If you have studied neural network, many of you might be knowing what is feed-forward neural network. So it is an example of your deep neural network. So backpropagation is a very common algorithm that we use in the feed-forward neural network. So backpropagation does not work well if there is a small number of hidden layers. So backpropagation algorithm works well when between the input and between the output, the set of hidden layers are too high. So this occurrence of local optima or minima is one source of difficulty in deep learning. And backpropagation error becomes either too small or the error becomes too large when there is a gradient issue. Okay, so now this is an example of your deep neural network. So the frame level decisions are averaged to get the artist. So you see, this is the input set of input layer. This is the set of output layer. Now these are the hidden layers. There are 1, 2, 3 sets of hidden layer, and now all are very much deeply connected to each other. Okay, all are deeply connected to each other. So, okay. So if you want a more detailed description, you can go to this paper of one of my students, myself and one of my students, Himani Shekhar Das, a deep dive into deep learning techniques for solving spoken language identification problems in intelligent speech signal processing. It is already published. So you can go through this paper, then you can have a detailed understanding of how the deep neural network can be used for understanding the spoken language identification problem and how you can use this one. So here you can see that in the deep neural network is used for doing the language identification of 8 languages. Okay, so there is something FR, I think it's France, Italy, JA, RU. These are the code names of different. So you can see in the paper, if you want the details of it, you can see in this Lopez has published this paper in 2016 for automatic language identification. There you can have a detailed description of how they are trying to find out, trying to identify the language. Like Hey is more recognized in ES language, paper. So here another work is given by Monica and Lakshmi Ganga Shetty. So 2016, they have also investigated deep neural network for language identification in Indian languages. So this is an architecture they have proposed for deep learning. This presentation detailed out of course for details requirements. So interspeech, it is published. Interspeech is one of the top 10 conferences of speech recognition. So their published papers are very good. You can go through those papers. So this is your convolution neural network. In the convolution neural network, there is a set of, this is a simple diagram of a convolution neural network. We give the set of inputs. There are feature maps. Then there's a convolution layer 1. After that, all the features are pooled together in one place. Then after pooling, it is again given to convolution layer 2. Then again, second pooling layer is formed. And finally, we get a, like that it will go on. Convolution layer 3, 4, 5, as much as required. And then finally, we will get the output. So this is convolution neural network. It is an example of your deep neural network. So in the case of deep neural network, there are different kinds of deep neural networks. So first one is your convolution neural network. Okay, so here also, as I've told you, we have worked on it. Kinds of deep learning techniques are given in details, that how you can use it for solving the spoken language identification. So it was published in Intelligent Speech Signal Processing. Myself and one of my students, we have worked on it. So you can go through these papers. We'll get a total idea that how to apply it in the language identification. So understanding the convolution neural network. So here you can see this is an input image. Suppose the input image is taken. So this is the size of it, 32 into 32 into 3. And this is the convolution neural network 1. Here they have taken the size as 28 into 28 into 6. And here now you can see it is reducing. Earlier 32, then it has become 28, then it has become 14 in the layer 1. In the layer 2, then convolution 2, it has become 10 into 10 into 16. Then 5 into 5 into 16. So here in the convolution architecture, what happens? It starts with a bigger one and it reduces. And in that way, the this recognition is done in a proper way.
But the third dimension is increasing.
Yes, third will increase. Third will increase and the first two will keep on decreasing. Actually, the more details is out of the scope of this this one. If you want more details, I have told you, you go through this paper, you will get everything. Every details will get here. Okay. So you can see this is an image, 6 into 6. For earlier it was, then it reduced 3 into 3, and finally it is 1. Okay. So in that way, finally it is 1 into 1. So the convolution neural network, it reduces the space. If suppose an image is there of 6 into 6, it will reduce, keep on reducing, and finally we will get a convoluted neural network. So this materials are given in the net also. You can find out and you can study this part. Okay, so I'm not going through much details of it. So what is the main aim of a convolution neural network? Convolution neural network, if the space is too big, suppose I am recording anything and the metric size is very big, because whenever we represent the speech after doing the feature extraction, you will get a kind of matrix. Suppose you want to work in a MATLAB, you are getting a kind of matrix. So size of the matrix is something 2825 into 12 or 28, or suppose 3895 into 12. So 3895, you can see it's a very big number. So what the convolution neural network does is that it tries to reduce it. First layer, if the size is big, second layer, it will do the size as half. Okay, like that, it will do the size half, and during the output, the processing becomes very easier. So that is the main aim of your convolution neural network. So here also one paper, speech emotion recognition using spectrogram and phoneme. It was published in Interspeech by P. Kumar and A. Tripathi. So if you want, you can go through those papers. You will get a more detailed idea of how to work with it. So here it is a LetNet. This the name of this architecture is known as your LetNet convolution neural network. So here it is one example which was given by Lee Kuhn in 1998 for 7-layer convolution neural network. Okay, so it is a 7-layer network, Here, what it does is that it repeatedly uses convolution and pooling layers. As I told you earlier also, the convolution, it is feature maps, and then it pools. Then again, it is using convolution to feature maps, and then again it is pooling. So here you can see, as you have told out, so this, you see 28 into 28, it is 14 into 14, and here it is 16. Here again 14 into 14, this one is again increasing, 32, 7 into 7, again 32, and finally we are getting the output of 10. So I can't go through much of the details because we have limited time here. So all the links are given here. You see this paper, gradient-based learning applied to document recognition. You can go through this paper for details of this Lee Kuhn, how he has worked in 1998. Another, these are the people are proposing this for the different types of convolution neural network. So LXNet convolution neural networks were introduced by Geoffrey Hinton group in 2012, and it was the winner of ImageNet challenge. So here main idea was building the deeper network by stacking many convolution and pooling layers. Earlier it was only 7 layers in the earlier model. Here it is saying that it is using convolution layers and pooling layers, lot many, not one, more than that. There is no limitations also how many it is using. So here it is using RLU activation, maximum pooling, normalization, and dropout. Here it is using after normalization, dropout to finally get the answer. So why it is doing all this thing? Because you see, whenever this concept of deep learning comes, deep learning is only applicable when your data size is too big. And now the situation is like that we need to apply a lot of deep learning because we are now working with big data. When we say we work with cloud, we work with big data, that means the sizable, we are more dependent. High we were using, so ML news does not well. To use the proper deep learning, and here it is written only dense, the data will be too huge, and those data will be handling, and we will find the is of network. Different kinds of, so that's why the more the data is there, the huge data is there, we cannot use SVM or the other technique. So during the time our deep learning comes into play. So if we want to do the language identification task, can only be processed through the properly through the deep learning techniques. And when we say that I am using a simple neural network, then you can, I will just give an example. You see, when I say that I am using a suppose this one, 2 hidden layers, all the hidden layers are using a deep neural network I am using. That means in this layer there will be thousands of hidden nodes, maybe lakhs of hidden nodes, maybe more than that. Here also there will be 1 lakh, 10 lakhs hidden nodes may be there. Here maybe 5 lakhs hidden nodes. So now you see, when we connect it, when one node is connected to 10 lakh nodes, again second node is connected to 10 lakh nodes, that means how much the processing time is increasing, because inside there is very complex communication going inside. side. Input is okay, output is okay. But when I am trying to connect 1 lakh node with again 1 lakh hidden nodes, again this second layer, third, it is not like the deep layer will have only 3. Here also these layers we may have 1000, we may have 500, we may have 1 lakh also. So now you can see that processing of this inner side, it becomes so complex. So to handle, if we use a simple neural network, then what will happen? The machine will never give you results. Maybe it will take 10 days, 20 days to give you the results. Or maybe it will not give also. It's not possible. So that's why we use different kinds of deep learning techniques, so that in between that work that it is doing, it becomes little faster. So these are the different techniques actually. If you want, you can go to those papers, you can easily learn how to apply those techniques. And so that's why, yeah, so that's why in these techniques, you see this box kind of things are made. So that means so much data is there, it is dividing the data into 2 parts, and then it is applying the LXNet convolution neural network, and then so many layers it is applying, and then finally it is max pooling, it is doing normalization, dropout, and finally it is getting the result. So it's a huge data. So the paper link is there. You can go through this one if you want more details of it. So GULE-NET neural network, it was introduced, okay, it was winner in 2004 to introduce different kind of size filters in the same layer. Different kinds of size filters we put, 5 into 5, 3 into 3. As I've told you, that the size is increasing. You are asking me the question. So you see, it is using, and it is having same layers you can pull from time to time. But you can see 8 into 8 into 2048. Okay, so this was your output, and final part, it is getting 1001 here, the result. So this is a very common one, VGG-NET convolution neural network. It was introduced by Visual Geometry Group at Oxford in 2014. So you can see these are all recent things, because the deep neural network, it is a very recently developed algorithm, recently developed model people are using, and now from the time to time people are coming up with the new kinds of convolution neural network which can be applied to do the processing faster. So it was also a winner of 2014 ImageNet challenge, and it consists of 16 convolution layers. The same way, 1, 2, 3, 4, like that, up to 16 convolution layers it will have. Here also it is using max pooling, convolution layers, and ReLU filters. And then it was a very big size, 224, 224. Then finally you can see in the result, it is 1 into 1 into 1000. So in this way they are doing. So, and this is also a very important one, which is known as your ResNet convolution neural network. We actually use these ones in our experiments. So you can use these models in your experiments. So it was introduced by Kaming Hee in 2015, and it was the winner of 2015 ImageNet challenge. Here it increases the depth, but here what is done is that you don't have to go through the depth one by one. You can skip the connections to avoid some of the layers if you want. You see, inside it's such a deep neural network. So many things are there, no? So convolution neural. So here you can skip. If you see that this part is not required, here we can skip some of the layers and we can go, so that the processing becomes little faster. So so it is less complex, okay, due to the skip connections. And here it is your Densenet neural network. It was again introduced by Huang in 2018, and it was made with the help of the dense blocks. So these are the dense blocks through which it is made. And here the main idea of the feature map was to concatenate and collect knowledge is made. So you see, this is an image input, and this is the convolution. This is the block, dense block 1, 2, 3, and finally the predictions that it is doing. So I can't explain you in much details because we have very less time and more data to complete. So I will request you, please go through these materials. The link papers are given. So whichever you want, you can just go through that part and you can have a details idea of the things. So there are different kinds of network. One is your long short-term memory, which is better, which can capture better than the long-term temporal patterns. And then we have recurrent neural networks. You know already what is recurrent neural network. And we have long short-term memory, where it is storing for a very small information, it is storing there. So this is an example of your LSTM, recurrent neural network. And then applications of recurrent neural network. Here we have image classification we can use, then image captioning, that which image is what, then we can use it for sentiment analysis, which is very much nowadays used in the Twitter and other things. And it can also be used for machine translation. NLP is very commonly used there, and leveling each frame of the video, there also it can be used. And long short-term memory in the recurrent neural network. So here it can be used for predicting the next word. As when we type a mail, you might have seen that always it gives you some options, and usually it gives us correct option only. That when I type how, then it will give us option R, is, like that. So we select the R, and then after that it will give the option as U. Then some options it gives us, and we usually select that one. So this is an example of your predicting the next word. So predicting next word, it is also used in your Google search engines also. So it is the counsel, it is the prediction, and here these are the inputs that we give, head, A, general, okay, and these are some of the hidden units that are used. And so each word is represented by the integer, and output is one vector. So here it is the output. So you see here, whatever the elements are there, you see some probability values are given here. 0.01, 0.2, 0.65, like that. Whichever is having higher probability value, that one is selected. So like that way, prediction of next word. So as I've told you that what are the challenges that are involved with the Indian language identification. So see, India is a multilingual country, and in India we spoke various languages. We have 17 or 21 is there, which are recognized by the Constitution of India. But apart from that, we have so many small dialects that are spoken. In the Northeast only we have so many language. So Census Survey of India 1961, it has identified 1652 languages among 880 languages are in still use. So 880 types of language we use in India. Maybe these are not recognized. Some small dialects also we are using in the different regions. So we cannot go for recognizing so many languages. So, but we divide into 2 to 3 parts, that how we can do the identification. So Indian languages, it can be broadly classified into 3 categories. One is your Indo-Aryan, 76.5% people are speaking that. Telugu, Tamil, Malayalam, Kannada, these are all Indo-Aryan languages. Dravidian language, Hindi, Gujarati, Bengali, Marathi, this comes under your Dravidian language. And Sino-Tibetan, only 3% people are speaking. This is Nepali. But what are the problems or the limitations? The limitations is that whenever we try to identify a language, there are different things which overlaps. Overlaps, like I say sun, S-U-N, sun, I'm saying in English. So sun in the English means Suraj. But sun, when you, because I'm not writing anything, I'm speaking. But when I say sun in Hindi, sun means sun 1975. Year. Sun in the Hindi means year. Sun 1975. But whenever I am saying sun in context of the Suraj, then the sun means different. So sometimes there are some words like that. There are thousands of words which sound similar, but they are different in different languages. So sometimes it becomes very difficult to find out the overlapping of phonemes. Okay, so like that, there are many. I'm just now cannot recall. This is I'm recalling. So many words are there when we try to work with it. There are many words which overlap. In Bengali, it means something else. In English, it means something else. And since we are not writing, because if you write, the give you the wrong results. So there are the problem is that there are a lot of similarities in the Indian languages. So if you see the Hindi, Gujarati, Bengali, Marathi, many things are similar in these languages. So a lot of similarity in Indian languages. Because of that, sometimes even in Hindi and Nepali also there are a lot of similarities are there. Sometimes it becomes very difficult to find out the meaning or find out the language that what the person is trying to say. So after going to the limitations, now we need to have the knowledge that whenever we want to work with any language, the main thing is that we need to have a proper database. Without the database, we cannot work. During the time I worked my PhD, I was not so much fortunate to get the database, because during that time this work was very initially started, and I did not get access, because during that time the database was not available only. Now this NIST LRA corpus published by the government, it is there. LDC call friend, you can use OGI 22 languages, telephone speech corpus. These are now available for Indian languages. But during my time, there were, because people were not working with this, so the Indian language corpus, official corpus, it was not available. But during my time, this TIMIT was available. But TIMIT is comprises of 16 languages, foreign languages. This Chinese, Telugu, France, German, America, like that. They are having the languages of those countries. But during my work, I just focused that why I should work on Chinese, Japanese, or Korean, or like France, German language, which I don't understand. I don't understand. I wanted to work with language identification. And another constraint with the TIMIT corpus was that if you want to download the database, then you need to pay. I had to pay some dollars. During that time, our salary was also very limited, and I don't want to spend so much money on buying the foreign database and working on it, which I don't understand. So during my time, I had to record. I had to literally record, and I have made around 5,000 speech corpus database by myself with the help of my students. Students helped me a lot. I took Assamese, Bengali, English, and Hindi language, because English, Hindi, everyone knows how to speak. And Assamese and Bengali are very common. Here many people speak. So I got hold of the students and I told them, you please make the database for me. So students helped me a lot. Each word they spoke 25 times, 30 times they spoke. If it is wrong, again I got hold of them. I told you, go and you do it. It's a project work you have to do like that. But they have helped me a lot. I made a database of around 4,000 samples, and then I applied the algorithms, and then I started my work. And since there is the same database, my students are also now using. So it was very tough during my time to work with it. But now you see so many databases are available. Even this NIST and all, they provide the free language corpus database. It's a government published database, which government is now providing. If you want to work, you can work with it. And these are the speech corpus, which are standard, which are available. You can go through it, you can download it, and you can work with it. And here also, there are some papers which are given. IIT KGP and MLILC, they have published a paper, and they have worked with 27 Indian languages for 27 hours. Actually, this is the database which is available with IIT KGP. If you mail them, they can provide you the database. And out of this paper was made, number 17, paper was made, speech database for language identification, and it was published in National Conference on Communication, IEEE. So they have worked with it. In the 2012, they have worked, and so there you can get a lot of speech corpus. Okay, so these papers, these are the link where we will get. These are the papers which are made from the different databases which are available. So we'll get a link. If you go to those papers, you can get a link of accessing those databases. So what is the problem is the existing speech corpus for Indian language identification. The state-of-art model for LID are data-driven. It is totally data-driven, and for that, it requires the large amount of data. During my time, you see this high-end GPUs were also not there, and data sets, actually 4,000 is actually a very small subset of data, because I have to do it. So, but when I have used this SVM and other models, my machine used to heat up, and one laptop has damaged while doing my PhD work. So during that time, the things were different. The processor speed was not so high, and the RAM was also very low. So it used to take a lot of time to give the processing. But now, since we have high-end GPU, CPU, whatever we are using, the machines, it's very high-end nowadays that we are using. Laptops are also very high-end. And we have these deep learning approaches and all. So we can use a very huge data, no issue. If you have a very large set of data, you can easily apply deep learning techniques and you can get the results. So these are totally data-driven. Once your data is changed, suppose now you are using 50,000 data, you will get certain kind of results. Suppose you are increasing it to 2 lakh data, your results will drastically change. So that's why we say that language identification is totally a data-driven. The more data you give, the result will be different. The less you give, the result will be different. So it totally depends upon the data. That's why we require larger data. The more data we give, the more the system will be trained. So recently, some of the challenges of LID are in the Oriental language recognition and language recognition evaluation. They released a large speech corpus. Okay, so they have made a large speech corpus. You can use the speech corpus, and a new large speech corpus called IITH-ILSC, which is having a combination of 23 languages of 103.5 hours. It was developed only for doing the language identification. So you all are lucky enough, because so many things now the government is providing, people are working. So you have to just grab those database, apply the standard feature extraction techniques, MFCC, LPC, whatever you want, and then you go directly to the deep learning techniques or whatever techniques you feel comfortable, and then you will get the results. So finally, I will summarize and conclude. And I think already it is, yes, or 15 minutes we have. So the similarity in origin and overlapping phonemes, actually it is a very big challenge in the developing LID system in Indian scenario. In the Indian scenario, it is a very it is a challenging task. And another task we can carry on is that if you want to develop the speech data set, that also you can do, because the data sets that are now available, these are for the standard languages. We can develop the data set for the dialects. Some dialects are there which are commonly spoken in some areas. So for the dialects also, the speech database can be made. So that's this is also a challenge in the development of the database and then availability of the standard dataset for working with the Indian languages. So deep learning based approaches, it has already shown a great promise in the Indian language identification. So as I've told you, grab the database, apply the deep learning techniques, and you will get a very good results. So already it has given very good results in the Indian language identification. But there are several areas of LID models which still lack a lot of significant work where you can contribute your work. So long-term temporal information, it may be either at the feature and model level, it have shown the better LID performance. And spectrograms are there which always show the good performance along with the feature extraction, okay, from different pre-trained convolution neural networks. And if the training data set is low, very low, the training data set that you're using is very low, then we use the transfer learning. This is a technique that we use when the data set size is very low. So these are some of our observations of the work. And these are some of the publications that the Shashwati Devnath and myself, we have done. This paper, these are the journals that are Himanish and myself, we have published in this language identification in the Arabic Journal of Science and Engineering. Another one was, this is a very standard conference of speech, International Symposium of Frontiers of Research in Speech and Music. There also one paper was published by Himanish and myself. And then here also Shashwati has worked on some of her work. And TENCAN, it is one of the top 5 conferences of speech, where we are very lucky that one of the paper of Shashwati was published there in TENCAN, multimodal authentication system. And International Journal of IJST, it's a Springer paper. There also Himanish has published his work. And like that, so these are some of our publications that we are totally working on it. And we'll be happy that if you are having any doubt, or if you want to work in this area, or if you want to do any collaborations in this area, I'll be happy to render my help or jointly work with you, or any kind of help. If I can do you with my materials or whatever is present there, I will feel myself that I'm very lucky to help you. And finally, I will end my presentation, and now it's open for questions. So please, you can ask questions. I'll be happy to answer your questions.
Madam, this is Dr.
Yes.
That gradient descent works for same for image processing and speech processing. I mean, speech data and.
Can you speak a little louder? I can't hear you.
Madam.
Yes.
Yes, madam.
Please put your mic closer to your mouth.
Yes, sir.
Yeah, much better.
Yes.
Sir, madam, gradient descent we are applying for image data and speech data. Will it work for same, or how the features can we are extracting in the case of that gradient descent while applying for speech and image data sets?
Yes, you see, there is not much difference. There is not much difference between the speech data and the image data. Okay, so it is almost same. Like in the image, what you have is that. Just a minute.
Yes, madam.
Some problem. Okay, so there is actually not much difference between the speech and the image data.
Yes,
Okay,
madam.
so but the feature extraction techniques are different. And because I don't work with the image data, so I am not sure what kind of feature extraction technique are applied on the image. But the feature extraction technique of the speech are, as I've told you, that LPC, MFCC, SDC, PLP. These are the different feature extraction techniques we use in the speech recognition, and then the modeling techniques that we use, like this one, SVM, ANN, deep learning. So that we can use in image also, that we can use in speech also. But the difference in the speech and the image is the speech is a wave kind of data. When we talk, there are a lot of frequency changes, and frequency change of the signal is there. So that's why what is done is that there is a lot of variations in the signal. Okay, so in the case of the speech signal.
What is
But,
exactly gradient descent, madam? What is exactly gradient descent does in the case of image and speech data?
Gradient descent, it is a part of the gradient descent, it is a part of your feature extraction. Okay,
That's all.
so it is it's a part of your feature extraction. Okay, so in the image, I am not sure because I don't work with the image, so I'm not sure about the image part.
Okay.
Okay. Any other questions?
Okay, so we will take one or two questions, then we will try to wind up the session. Audience, please, one question.
Good evening, ma'am.
Good evening.
Ma'am, I want to ask you, ma'am, what are the toolkits we can use for speech translation?
For
speech translation.
Speech translation. Toolkits. Means you are talking about how we'll implement.
Yes, ma'am.
Yes, the MATLAB is the through MATLAB you can do the implementation because the speech data, it is actually very huge data which we have to handle. So through the MATLAB you can use all deep learning techniques, ANN, everything you can use in the and we usually, my students are working with MATLAB only. So we actually work with MATLAB. Maybe there are other tools also people are using.
Okay, ma'am. Thank you, ma'am.
Any other question?
Okay, so we will have one more question. Anybody? Any questions from the audience?
Madam, while processing speech data, usually what are the, what type of data we are removing? Like if you take in image case, we are removing noisy data, redundant data, inconsistent data. Same way, in speech data, what are the pre-processing techniques we are using in speech processing?
I think I answered your this question. That pre-processing techniques are this one: LPC, MFCC, SDC, PLP. These are the different kinds of pre-processing techniques we use for removing unwanted things from the speech. So in the speech, you see when we record, there are a lot of noises are there. Lot of noises. Yes. Then when we talk, there is a voice of the fan which is moving. So there is a microphone disturbances which are recorded. Okay, so many things are there which gets recorded along with the voice. So that things need to be removed. So there is a noise removal part also which needs to be done. And only the important information is extracted.
Okay, madam. Usually we are using in image processing binning and box plot techniques we are using. In the case of speech also, it will apply, madam? No?
No, I never heard. No, it is not applied on speech. In speech we have separate techniques: MFCC, LPC, SDC, PLP. These are the techniques we use for speech.
For removal of noisy data.
For removal of, yes, for removal and extracting the important features.
Okay, thank you. So now we would like to thank our speaker for the nice talk, and we would like to welcome our next speaker. Once again, thanks the speaker. Dr. Pinky Roy,
Yeah. Thank you.
and a wonderful talk. We had a very we enjoyed your talk today. And
Thank you.
Chaksi, are you there?
Yes, yes, sir.
Okay, so we have Dr. Samaria with us, joining from Houston today for the next session. Saksi, please go ahead.
Yes, sir.
Hello, Dr. Solario.
Hi.
Hey.
Hi, madam. Hi, madam.
Oh, Saksi, please
Hello,
go
good
ahead.
evening, everyone.
We have 5 minutes time or some? Okay. Yeah, we have, yeah. Saksi, please go ahead. We have.
Okay. Yes, sir. Good evening, ma'am, from India. It's my honor to introduce you. Dr. Thamar Solorio from University of Houston, USA. She will be talking on adding flexibility to neural language models. Dr. Thamar Solorio is an assistant professor at University of Houston, Texas, USA in the Department of Computer Science. She has secured over $3 million in funds over several research grants, including funding from NSF and US Department of Defense. Her research deals with the analysis of spontaneous language samples. She works with written language mostly, but some of her works also deals with transcriptions of spoken language. Her main research projects can be categorized along these lines: forensic linguistics, including authorship attribution,
I'll give you
profiling
address.
algorithms,
Speech recognition.
detection, computational linguistics for the analysis of code switch data, health informatics, clinical NLP, the use of NLP in language assistant for the clinical purpose. Now, may I request you, ma'am, to kindly start your keynote presentation.
Thank you. So we're ready to go. Let me
Yes,
see if
please go ahead, Dr. Solario.
okay, let
Please
me
go
see
ahead.
if I present now, right? I go to present now.
Right. Yeah.
Okay, so select entire screen. Okay. So please let me know if you're not seeing my my intro slide. Very happy to be here today. Good evening, everyone. Thank you so much for the invitation. I always like to have the opportunity to talk about the research we do in my group. So yes, as it was mentioned in the introduction, I'm going to be discussing some of the things we have done in my research group that are aimed at increasing the flexibility of neural language models. So as most of you know, word representations or continuous word representations are very common in any NLP pipeline system, right? They allow us to have exploit meaningful information, semantic and distribution information of words, and they are your common ingredient in any deep learning or machine learning pipeline today. But they have some limitations, even though they're very powerful. The different word embedding representation based on neural models have different limitations. So if we go back, for example, to the very first ones, the word to back and globe embeddings type of things, these were the first continuous representations proposed in our field, and they certainly increase the performance of a lot of systems based on them, but they have this limitation of the out of vocabulary words, right? This initial embedded representations were trained on large amounts of data, but if your test data or data for which you need to extract these word embeddings was not observed during the training of these models, then that means that you don't have a vector for these words, and you either drop them completely from your textual representation, or you replace them by this special unknown token, right? And so this is certainly not ideal, because as we know, language is alive and continues to change, as well as language adapts, right? For example, different genre like social media will have a lot of new vocabulary, not necessarily new concepts, but new spellings and all of this. And so these initial models will have that limitation. Then after that, it came fast text. Fast text was proposed as a solution to these initial word embeddings, in the sense that instead of having a single vector representation for each word that was actually fixed, right? That's what your word back and globe were learning. They actually tried to learn a representation for words based on the set of engrams, character engrams in the word. So the idea is to try to exploit some morphological information from the word, as well as, if we see an out of vocabulary word, a word that I actually didn't see during training of my models or my word representations, I could generate a word representation based on the character engrams, because fast text will learn the representation based on the engrams of the word. So hopefully, or very likely, you may not see, the model may have not observed the specific complete sequence of words, but the chunks, the character engrams, were more likely observed during training, and then could be leveraged to generate a word representation. So this is more flexible, but it has a problem that is not contextualized, right? You still were getting only a single vector per word, and that has the limitation as well that if you have polysemous words, this is not captured, right? Most likely your model was generating a vector that is representing the most frequent sounds in your corpus. Then came ELMO, right? These contextualized representations, where they have the best of both worlds, almost. They generate word-based representations, but they are learning from the characters in the word, and they are contextualized. So which means that ELMO was learning, generating on the fly, word vectors that are depending on the specific context of the word. So if the same word appears in a totally different context, then the resulting representation from ELMO was going to be different, right? Which is great. It is getting to a better place. But this is still monolingual, right? This was still ELMO is still learning monolingual representation. So we had to do code switching processing, for example, which is some of the things we do in my group. Then you couldn't use ELMO because ELMO was either trained on English or Spanish or Hindi, but maybe not the combination. And then also after ELMO came about, we also have the transformer-based models, which are the most commonly used right now. Your BERTs, Robertas, and the cousins of them, and GPT-3. And in these models, these transformer models generate word-based representations, and in order to deal or handle out of vocabulary words, all of them use this byte pair encoding algorithm, right? And this byte pair encoding algorithm is learning sub-word representations, so that if you don't have the exact word in your initial table of embeddings, because you didn't observe it during training, then you most likely will have the sub-word pieces, right? And in some cases, these models will fall back to actually single character representations, because if the sub-word pieces are not found, then you will make it into smaller chunks until maybe all you have is your character-based representations, and from that you feed that to the rest of the model. And this is a very efficient process, but then this is also disregarding morphological information. So it's just optimized based on the frequencies that you have in your training corpus. So I'll talk a little bit more about how we try to solve or improve on these processes during the rest of this talk. And so why do we care about doing these things? Why are we trying to add flexibility? Well, because what we do in my research group is we try to process data from social media. And so here's an example of the things that we see in social media. We see very flexible spelling, right? We see adaptations or phonological modifications to the words, right? And we also see code switching. So we see that in social media, a lot of people are going to be mixing languages. And so I care about being able to process the data as is here. And the current models will have limitations in that respect. So let's see what are the things we did first. I'm going to talk about what we did in the context of leveraging English models to process code switching data, and then evaluating the applicability of this into two specific tasks, name entity recognition and power speech tagging. So here's a diagram representing what we try to do. The main idea for this is that we have code switching paired with English, and if we do so, then that somehow should allow us to leverage models or information in English, while at the same time we try to learn something about the other language, right? And so here we want to use morphology from a model that is already trained on English, so that the model recognizes English words, but at the same time is able to recognize or learn morphology from other languages, in this case, Spanish, Hindi, and Nepali. So we start with an ELMO embedding. Remember the contextualized ELMO embeddings. We decided to start with this because precisely the advantage that ELMO has, that word representations are formed from character engrams. And so I think our assumption was that because morphology is important, if we start with character engrams, then we allow the model to detect morphology from different languages. So we start with an ELMO pre-trained model. We do some adaptation to it here. I'll talk about what we are going to do here. We use multitask learning and we rely on morphology. Then we create a version of ELMO. We call it CS adapted ELMO. And then at the end, we take this pre-trained model and we fine-tune the model for our desired downstream tasks. In this case, name entity recognition and post power speech tagging. So this is the diagram overview of the actual ELMO model. I want to highlight that if we remove this pinkish box, everything else here is your standard ELMO model. Okay, this is, your CS almost starts from tokens generating your character engram convolutions, then you feed it to the hyper projection layer, and then to your BioLSTM layer, right? And you generate your presentation. So this is your traditional ELMO. We just add another block here that we call it the enhanced character engram. Oh, sorry, wasn't trying to do that here. And for this new module that we add, this is where we're trying to make the model learn something about the other language. But so let me go back to here. So this is what we do. We introduce an adapted ELMO that we call CS ELMO, and we use multitask learning to train this model. So our first objective is to do this this prediction for language identification, where for every token in the input, we want the model to predict if it's language 1, language 2, if it's mixed, if it's ambiguous, foreign, identity, other, or if it's unknown, okay? And the other learning objective is simplified language identification task, we call it, where we want the model to predict if this is language 1, language 2, or something else, right? So the emphasis here is that we want this character engram representations. We want to force the model to learn from these representations to actually distinguish what morphology dictates or what morphology signals if it's one language or the other. Okay, this is what we do here. So the rest is a standard model architecture where we have your ELMO representations and we concatenate other word embeddings like embeddings from Facebook and Twitter data. We give that to a BLSTM layer, and that in turn is concatenated to this representation of character engrams, and we feed that to your CRF, and then we predict this task, right? And so the loss of the overall model is the combination of the loss of the two different tasks, right? Plus a regularization term. And each task in turn is a negative log likelihood of these particular classes. Okay, so let's talk a little bit more about this pink box here. That's the overall model. Now we're zooming in into the specific changes that we do. So this is the enhanced character engram module. What do we do here?
Excuse me.
Yeah.
Yeah, in the previous slide, during the loss objective, in the second term, there was beta. Why there is beta for the second task, not for the first task? I mean,
yeah,
some
so it's just
for the first task.
Typically when you have multitask learning, you want to have a weight associated. You usually have a weight. Yeah. So because we want to. This task is important, but it's not as important as this one. So this beta parameter is a weight that we set so that this task is not having the same influence into how we tune the parameters. So this is, so in other words, this has, you can consider this has a weight of 1, right, for the loss of this task. And this has a weight of 0.6 something. So that the loss of this task is not as important. Right, so the main task is this, to do this particular one, right, for the entire model, and then we just underweight the loss function for this particular one, right? So that's just a common thing to do with when you do multitask learning. You assign weights to your different losses. You can have them do the same weight, but if we have them with the same weight, that means that they are equally relevant and they influence how you tweak your parameters at the same rate, right? But if you see here, the model is only, this part of the model is only seeing these parameters, right? It doesn't see all of this. This is only seeing, is only affecting the outcome of this one. So that's why we underweight, we underscore the loss function for this particular task. Does that answer your question?
Yeah.
Awesome. Okay, so this is what we have inside of the character engram model. So Elmo does convolutions at the character engram, right? So this is the same thing we do here. But what we do is that we add to this representation, we add position embeddings because we want the model to take into account where in the word are those specific character engrams. And this is because many languages will share characters or alphabet, like take, for example, English and Spanish. But the combination of characters may vary at some very critical positions. So for example, here, we have in English the sequence of characters ing, right? And that's very telling of an English word. But in Spanish, we will not observe a word ending in ing. That would be pretty odd. So the fact that this sequence of characters is observed at the end of the word is important, right? Because in Spanish, this sequence of characters actually appears. It's a valid sequence, but it's most likely at the beginning or in the middle of the word, never at the end, right? So this is what we try to do. So we start with the convolutions for the sequence of character engrams, right? We do bigrams, trigrams, fivegrams, right? And then we're going to add to this, these are your character convolutions. We're going to add to them position embedding information. So for each of these convolution engrams that we feed this to the position aware attention module, we're going to add position information like it shows here, right? We just want to encode where in the word is that engram happening. And with that information, we want this module to actually learn an attention weight that is based on position. So in other words, we want this module is going to be fed all the convolutions from the character engrams for that word, but then we want them to be weighted according to the different position right? And after that, we give that, so we have hierarchical attention. We have attention at the engram level based on position information, and then we're going to add attention at this level. What is happening here is that Elmo will generate convolutions for all your n-grams, bigrams, trigrams, 4-grams, and etc. And then it's going to combine, so Elmo typically combines these to do your word representation here, right? But we want instead is, we want the model, this enhanced module, to actually learn whether your bigrams are more important than your 4-grams, or your trigrams are more important. So for every word, we want the model to learn which specific n-gram is more important. So that's why we add an attention mechanism, and that attention mechanism allows us to generate the final word representation, the one that is going to be fed here, and the one that is going to be projected up the chain in the Elmo module. And then that's why we feed the model. So that's, and this is just to highlight, this is, we use this representations to do the simplified LID information, and then we feed that to the CRF model. Okay, so here are some experimental results that were presented last year at ADCL. So we evaluate here language identification on 3 different language combinations: Spanish English, Hindi English, Nepali English. This is the LID system that we use, so we compare with state of the art for those that for which we have numbers. And these are your F1 scores for language 1, for language 2, and this is your weighted average F1 score. Okay, so ours, this is the result of using the enhanced Elmo module. Okay, we call it experiment, but this is just the module that I just explained. And as you see here, in all cases, we outperform the state of the art using our embedded representation. And so these are encouraging results. Like, we don't, like here in this case, for example, for the module from Diab and colleagues, for language 1, or F1 score is not outperforming, but the weighted F1 measure that combines all of it is still larger than what's presented in state of the art. And I think what's more important is the trend that for 3 totally different language combinations, the only thing that they have in common is that they have English, and that's why we can use Elmo, is that we're getting better results, right? Whereas this particular, this is the same system that works well for these 2 language combinations, but for this one, we have a different one, right? And so these are different models, whereas our approach is the same approach. It doesn't change regardless of the language. Now, what happens with other tasks? We also evaluate, and remember, the goal is to take advantage of English resources, models, pre-trained knowledge, but to do downstream tasks that have mixed language, right? So here are results for Spanish English and Hindi English. The table on the left shows results for name entity recognition. The table on the right shows power speech tagging. The paper, of course, has the full set of results. I'm just showing here a subset to highlight the results. And this is the architecture that we use. This is the diagram that is shown here. Experiment 5.1 means that we have no code switching knowledge. So this is just your standard architecture. It doesn't have this part. It doesn't have this box, and it doesn't have this part. It just have the CSLMO as it is, and these are the results we get. Experiment 5.2 has code switching knowledge and is frozen. That means that we use this model with the LID language identification task. We train the model with that task. Then we freeze these parameters, and we fine-tune the last layer to do named entity recognition or power speech tagging. Okay, this is what we have here, knowledge frozen. And experiment 5.3 is when code switching knowledge is trainable. It's this setting, right, we use our enhanced models that were pre-trained for the language identification task. But during the fine-tuning for the downstream task, we keep tuning these parameters. So these are learnable. These are still learnable. They're not fixed. And so these are the results. Then we compare against state-of-the-art results. And in both cases, we are able to outperform to contribute a new state-of-the-art for the task. The difference is that for the different language combinations, we have either the frozen version or the unfrozen version that is giving us better results, right? But the model is still working better regardless. So what is the main takeaway from this part? I guess it boils down to the bottom message, I guess, the take-home message is that if we do pre-train knowledge, like in the case of leveraging a model like Elmo, and we do a small adaptation to allow the model to learn a second language, then these can actually replace what we used to do in the past of doing language-specific and handcrafted features in order to process code switching data, mixed language data, right? So this replacement is much more efficient, right? Because we don't have to think about features and we don't have to adapt the features to the specific language combination. So, and of course, it's not a silver bullet. It will not work in all cases because it relies on being able to exploit a language that has a lot of resources like English. If you move away from that, then all bets are off, right? You will have to have the ability to have large amounts of data to train these models. All right, so that was Elmo, right? But then of course we know that the more powerful word representations right now are based on transformer architectures, right? And so how do we work with transformer architectures? The main issue we were having before we explored and delved deep into transformer models was the fact that your Bert Robertas and all, they start at the word, they give you word-based representations when they start. They don't start at the character level like Elmo did, right? But then if we go deeper into the model, we go to the bipair encoding, we can actually work with subword pieces. So just a review of what happened inside transformer-based models like BERT, Excel, Roberta, and all of the, like I mentioned at the very beginning of the talk, they rely on the bipair encoding algorithm called BPE in order to handle in an efficient manner out of vocabulary words, or to manage reasonable dimensionality for what you keep with respect to your table of embeddings, right, that are the very beginning. So what happens, for example, with this, here's an example of how the BP algorithm works. So say you have as an input a sentence, some infrequent words, and for some reason the word infrequent is not part of the vocabulary of your initial embeddings into these models. So what the BP algorithm does is that it fragments these words. Say, I don't have an entry for this, so I don't have a representation to give you. So what I want to do, I want to break down this word into subword pieces. So we have an in here, then we have the F by itself, and then RE, and then the rest of the word, right? And the next word I do have it, so here's your word, your word, right? So these are what we call our subword pieces. And again, it's a very efficient way. All of these models rely on the BP algorithm. The problem, though, is that it's just not taking advantage of morphological knowledge. It just does a brute force fragmentation that is actually based on the data, the original data that was used to generate the lexicons, right? So based on frequency. And if you don't see, for some reason, the sequence of characters or the word that you want to represent, it's going to be broken down. And so that's not ideal, right? Because, for example, if we look at the word we can very quickly think of a much better fragmentation, right? So if it were up to us, we will probably fragment this word into the IN, and then we'll leave the rest intact, frequent, because most likely this entire fragment is part of the lexicon, right? Frequent is a very frequent word. But that's not how the DP algorithm works. It will just fragment based on the optimization process and based on your corpus, the statistics of your own corpus. So we want to work with this process and make it more flexible. And what we do here is we introduce a character to subword model. We want to replace your embedded table from BERT. So this is your traditional embedded table from BERT. This is the outcome of your BP algorithm. When you have a word, you want to extract the embedding representation from your lookup table in BERT, and you generate an embedding, right? And so we introduce the character to subword model that is also based on a transformer architecture, and we want our character to subword model to emulate the embedding that you will get out of your embedding table from BERT. Okay, so our module is going to have some differences, but one of the most important things that we want to have is that this module has to be a replacement from your embedding table in BERT. It has to be compatible, so that we want a drop-in replacement in BERT or in any other of your transformer models, so that you can just remove their embedding table process and put ours, plug in ours, right? So this is what we want to do here. This is the embedding table from BERT. You have your subwords, your types, and your positions, and then you feed that to the transformer, right? So we want to get at this box here. And so what we do is that we're going to train this transformer model using this loss function. That is a combination of 4 different terms. So I'm going to explain what we do here. The first term, this is going to be measuring the distance, the cosine distance, or the angular distance between the embedding generated by our character to subword model and the original embedding that is returned by your BERT model. Okay, and so what we want is we want our character to subword model to be as similar as what you get from the original BERT, the outcome of your BP algorithm. Okay, this is what this last term is actually doing. Then we have your cross entropy loss. This cross entropy loss is going to force the model, our character to subword model, to be similar in the sense that once you get your representation here, then you want the model to be able to predict which word originated this embedded representation. And this is what you're measuring here. The cross entropy is predicting what is the original subword that came out of this, okay? And then this third term, NBR, is a loss function that is based on distance, mean square distance between the closest embeddings to E and those neighbors and the distance to the generated embedding from the character to subword model. Okay, so again, we want the space, not just that these vectors are similar as possible, but also the embedding space. We want it to be similar, right? So that's why we look at the neighbors, right? We want the distance to the neighbors, the closest neighbors here, to also be the closest neighbors to this embedding. So we respect the entire distributional space. And then lastly, we have a regularization term, so that the dimensions of the 2 embeddings are similar. The magnitude of the embeddings is similar, right? Because nothing is preventing that the magnitude for this vector is different. We're all good? So far, so good?
Yes.
Okay. Now, once we are able to do that, we can actually modify our transformer model to be more flexible. I'm here starting.
Yashvardhan?
Yes. Yes. Please go ahead.
Okay. Is there a question or someone has a question?
No, please go ahead.
Oh, okay. So then, how do we add robustness? So this is not, our characters of word model is learned to emulate the embedding table from BERT, but how is that better from what we want to do? Well, it's going to be better because we add this additional process here. So for every word that we have in the corpus to train the embedded representations, we're going to modify the words so that we have, we introduce typos, we introduce repeats, and we swap characters, or we drop characters, we toggle characters, or we add punctuation marks. So that means that business is going to be fed into this model, but also the word modified by all these different processes is going to be fed into the model. So we want the character to support model to be able to still recuperate the same, the similar embedding space, but when the input is different, right? So when you have slight changes in the spelling that are very reasonable, so that the model can learn with these flexible representations. So here's an example of in and out of vocabulary words. This is your multilingual BERT. So we're working with multilingual BERT because in the end, what we want is to process code switching data. So if we take as a starting point, multilingual BERT and the embedding table from multilingual BERT. So if you feed the word business to the multilingual BERT, to MBERT, the closest neighbors that you will observe or that the model will give you are these ones. And these are very reasonable, right? So this is just the same word but with capitalization. And these are words in different languages, like this one, but they're also similar to the original word. So this is very reasonable. This is what our character to subword model is doing here. If you give this word as input to our character to subword model, these are the sequence of words that will give you as the closest neighbors. And as we can see, it's actually very similar, very much aligned to the original MBERT model, which is good because that's what we wanted to see. Now, this is what we see if we have character to subword plus the noise that I mentioned. So if we add the transformations that I mentioned and we feed those to the model, this is what we get as the output. And these are other examples. So if we change the word with some small modifications at the character level, like here, this is what we get as output. And it's very reasonable, right? If you get this business that is weirdly spelled, you still get very reasonable neighbors. And just as a reminder, if you give this to your MBERT, it's not going to find it because it's not going to exist as a whole word representation in your embedding table. Then you will need to fragment that, and who knows what it will give you as output, right? So this is just to show that at least here the character to subword model seems to be working and doing reasonable. Here are some other character to subword plus noise. Here are some other representations, right? And the list of words seems very reasonable. Now here's a pre-training. So we have to pre-train our embedding, our embedding table, right? And so here's what we do. We use the same language modeling objective that is used within BERT with the masking process. So if this is your input sentence, I speak Espanol, this is your BP tokenization, right? We're going to take these fragments. And so we do a masking process. We choose 50% of the subwords. So for this example, let's look at what will happen with this word. So we're going to choose 50% of the subwords. So these are all your subwords, and we're going to take 50%, so 15%. So that's that. Then we're going to mask 80% of the characters. So in this particular subword, we're going to randomly select and mask 80% of the characters. So here's what happens when we mask 80% of the characters. Then we randomize 10% of the characters. So that means that we transform them somehow with our process. And then we leave 10% of the characters in my subword unmasked. So this is the example of what will happen in the end. The masking process is complete here. And this is what we're going to be give the model to predict. We want the model to predict the characters that have been masked, right? When the masking process is complete, that's what we feed to the model, and then this is what we're training. Everything else is propagated at the model, but this is frozen. This is just as it is in the original Ember model that has already been trained. We're just changing this part. We're just training this particular module. Now, let's see what happens when we introduce this and we feed it up the pipeline for a transformer model. So we first have to pre-train, right? Our character to support model is pre-trained on Wikipedia data. We're using 1 million samples of 512 words in all these languages. We use distributed training over 32 GPUs. But one thing that we would like to clarify is that there's no need for extensive pre-training because we're not pre-training the entire Ember model, right? We are actually starting already from the embedding table and the pre-trained model from Ember. Ember, we take that and we just change it but we start with the parameters from Ember. So there's no need for either a huge amounts of data. There's no need for a lot of epochs, right? Because we're just fine-tuning a specific part. And so we have, we test our approach on the Lindsay benchmark on different tasks. And so we explore using our character transformer model in 2 different ways. So one is full, what we call full. And the full means it's the full replacement of embeddings, right? So this is your Ember architecture. This is our character to support. So basically we replace what we have here in Ember and just put our module. And then everything else is left as your original Ember. Remember that this can be used as a drop-in replacement for an Ember fully trained. And we do the hybrid mode. In the hybrid mode, if the Ember has the word representation on the embedding table, as it is like the full word exists, then we take that representation. But if the full word does not exist, and then that means that the BP is going to kick off, right? We're going to be giving a representation for the word based on the subword pieces, then we don't take those. And we take our character to subword because the assumption is that our transformer character to subword model is better at extracting meaningful information from subword pieces than the actual original word. Okay, so this is what we're testing, the full mode versus the hybrid mode. And of course, comparing against Ember. Right, so these are some of the results that we get. Our best proposed model, so this is our subset, right? There's an archive preprint where we show the full set of results. And so the best model that worked for us is a hybrid mode. So we back off to take our character to subword representation when the full word is not present in the embedding table from Ember. And as you can see here, the average for all these different tasks. So this is, again, the summary of the results. Our proposed model is much better than Ember, right? This is a multilingual BERT. And so here you can see individual results for different combinations of languages: Spanish English, Hindi English, Nepali English, Modern Standard Arabic, and Egyptian Arabic. This is for language identification, for power speech tagging, and for named entity recognition. Okay, so for some language combinations, this module is actually much better, like significantly much better. The improvements are larger than what you see in others, and certainly this is the case for Hindi English. And what is happening here is that some of our data is transliterated. So it's not using the Vanagar script, it's transliterated using the Romanized encoding. And so your Ember is not able to take full advantage of the knowledge from Hindi because your Ember is trained on Hindi data that is using the Banagher script. So we believe that our model is actually leveraging the ability to learn new representations that are relevant for Hindi, even when it's Romanized, because this model doesn't care, right? It doesn't really know. It's just learning what representations can generate for specific sequences of characters. And so, whereas this model is not. So I think this is one of the reasons why this model is better. But the model works better in any other language as well, right? Different languages.
Excuse me, ma'am.
Yeah.
In your previous slide, in your implementation, since this model has been not trained from the scratch and it is pre-trained, so it has been used from the Embed pre-train. So I guess the word must be looked up from the embedding space. But in the Embed, I think there might not be any character lookup table. So suppose if but your system is for also takes in consideration of the character. So what will happen if I have to look some embedding space, embedding factor with respect to a character, single character?
Single character. So remember that, just to clarify, so our character-to-word model does begin with the embedding table from Embed, right, or from whichever model you want to use for. But the model is also trying to generate new representations, right, based on so the model will be able to generate representations from other characters that are not part of the embedding table. So when your Embed does not have the character you're looking for, then our character-to-word model will generate something, right?
Okay, ma'am. So, like in the Embed, the embedding for the character, if it is not present, then your model will create a new embedding for this one. Learn a new embedding for a character.
Yeah. So this is So this is what we do here. This is what we do here, right? When we generate different combinations and we feed them to the model, you're still going to generate something. Now you're right. It's not going to be almighty, right? There may be some combinations or some characters that do not exist, right? Because in the end, we're still tied up with what we generate here, right? In the end, there's still also an embedding table that is being generated. And if we have an embedding table being generated, that means that it's fixed, right? That's your question, right? Oh, your sound is not coming out right. I'm sorry. Can you repeat?
As far as I think the vocabulary are already predefined, they are fixed. So I think that the dynamic learning of vocabulary, I want to know if the vocabulary is already predefined for each character, or it is learned during the training itself.
Right. So this is fixed. You're right. This will be fixed. But we're introducing new inputs to the character-to-word model, right? They're still going to be attached or like associated to the clauses that we have here. But as the input model here, because we're changing and we're adding and we're replacing to this particular one, so this will have a lot more, the table for this one will be bigger, right? Because we're introducing changes and we're introducing new word pieces.
Okay,
they are still going to...
Now I got it. I thought that I was confused. Like you're saying that you're not training from the scratch, so I didn't consider about creating a vocabulary. So indeed, you are creating a vocabulary of the character and using the previously created vocabulary of the Embed Okay, now I got it, ma'am.
Yeah, so it's still going to be limited from what we see here, right?
Okay.
Because in the end, this has a lot on how our loss function is dictated by this, right? But it is much more flexible. And it may happen that there's something we don't have in the embedding table. So it's certainly not infinite, right? Okay. Let me know if you have further questions. Very good question, by the way. All right, so we go back to the results. Yeah. So there's an archive paper if you want to read more about this. But so far it seems like it works better. My impression is if we had all the resources and we had all the data, we could probably do even better with this character to support, right? If we were able to train from scratch. But we don't have resources or the time to put machines to do that. So we can do well with with these particular modifications. And so as takeaway messages, so where pieces can degrade the meaning of sentences for rare words. This is what actually happens in the current models, right? If you have a rare word or an infrequent word, or your test data doesn't really match what the models were trained on, your software pieces are not going to have a lot of semantic value, right? However, these models, we know they work and they are robust because they just have tons of data, right? And so they sort of are robust to some sense, right? Characters are more flexible and can overcome typos, misspellings, and rare words, which is what we try to do now. And characters of word representations can be adapted to pre-trained models. And it's just a drop-in replacement. So you can actually take this character to word and this idea and use it in any of your transformer-based models, right? Because it starts in builds on the embedding table of your underlying model, right? And you just plug it in and use this as a replacement. Now, the last topic I wanted to mention very briefly because we're running out of time, I'm assuming, is what happens when we have topic changes. So this is not the same, that this is going into a different direction. So one of the things that we have, even if you have your pre-trained models, is that data like social media, they are very volatile with respect to the topics that are being discussed, and they're very rich in the vocabulary, very rich on what is being covered. And so any machine learning model that you can think of will have this problem of language drift, right? So what happens, and this has been identified before, is that your models are going to degrade over time due to this concept of temporal drift. And so here's a graph that shows, your flare and globe embeddings from a paper last year that shows that if your test data is new, say your test data comes from 2019, your training data is from different years, the closer your training data is to your test data, then the better your model will do, right? And the further apart, like the larger the gap in time, your model is going to do less well. This is the idea of language drift, right? So the vocabulary changes, and that's certainly something that happens. And so it's very expensive. You think about a live system, it's very expensive to keep retraining and retraining and labeling lots of data and retraining your model to avoid this. So we try to do a little experiment here with Twitter data in particular. So instead of just randomly selecting data, newer data, so that you keep your model crisp, like we mentioned there, so you retrain your model. You have to retrain the model anyhow, but can we do it in an efficient way? Typically, we just randomly collect data, we annotate, and that's it. However, if we think about how Twitter works, what if we focus on the data that tends to be, or there seems to be training data, right? What if we take advantage of the knowledge that we have from Twitter so that we can actually guide the process on how we select data? And this is what we do here. So we are going to grab newer data and we're going to calculate some statistics, basically frequencies of engrams, right? And what we want to know is which are engrams that have the largest difference in frequency with respect to my old data. So this is frequency of the engram in my recent sample, frequency of the engram in my previous data or my old data. And this is just normalizing with a small constant so that we don't have a division by 0. And we use this score to rank n-grams in the new data. And we're going to select data to label based on this score. And this is just a very simple trick to, what we try to do is, can we use trending information? If we use trending information, do we get better results? These are some of the results from what we do. So the gray plot is the temporal data. So what this gray data is doing, every data point here, we grab 100 samples. And then here we grab 100 samples from my oldest data point. Here we grab 100 samples from the newest data, right? But every time we grab something, we do it randomly. And yes, it improves, right? The curve is always going up because it is reasonable, because at every point in time, we're getting data that is more temporally closer to the test data. But if we use the trend information, like what we propose, the gains are much larger for the same amount of data. So instead of selecting randomly, we're going to select based on our scoring function. And that gives us better results, regardless of your model. So this is, a very simple idea that would help us to retrain our models to avoid temporal drift, but it does it in a very efficient manner. So some discussion points about this is that, we tend to do research in NLP with benchmark data that is 15 years old, sometimes older. And then we expect that those models are going to perform well when we create a live system, right? So that's not how it happens. It's probably time that we start rethinking how we benchmark data, how we benchmark our systems, and then we also think about, things like temporal drift, right? Models are very sensitive to diversity in class instances, diversity in distributions, and so if we want to do some adaptation that is efficient, then we also will be better off if we think about what kind of data we're using and how we can use the properties of that data to guide model adaptation. Anyhow, so final thoughts. This is what I just mentioned about data sets. We need to have better ways to benchmark. We need to think about how all data is leading what we do in terms of publications, but that's very outdated data. Should we start, discarding some of these data sets and push our community to create newer data sets? Future work include noise-based and phonetics and character glyphs. So how can we do phonetic information? So a lot of the misspellings are guided by phonetics. So instead of just randomly switch characters, maybe we can replace them based on phonetics, right? And align the characters to word representation across languages so that we do pre-training with more languages simultaneously. So these are the things that we would like to do in the future. Last but not least, all the work that I have mentioned is actually not done by myself, right? It's done in collaboration with a lot of people, a lot of brilliant people, current and former students and collaborators. And this research is sponsored by the National Science Foundation. So I would like to take this time to thank my sponsors and my collaborators here. And lastly, thank you so much for your attention. Here are some links. You can follow me on Twitter, follow the website, or get the code if you go to our website. And with that, I'm good. If you have questions, I'm happy to take questions.
Audience, questions if you have. Sakshi, are you there?
Yes, sir. Any question from the participants?
I'm still here. I just wanted to to see if I can see people raise hands or whatnot.
Sir, I think there will be no question.
Okay, so just one question from my side. So, something about of all these models, apart from the proposed model, if GP3 was attempted for code switching at some point of time?
No, so GPT-3 has not released, has not give the ability for people to tweak the models, right? I think all we can get are the embeddings.
Okay, so if once that is there, then probably we may try out for some of the data sets.
Yeah, but if the model is released like in the other cases of Roberta, no, you should be able to do the same thing we did, right? So just start with the embedding table from that transformer model, then do what we did to with the character to support model.
Okay. Okay, so is there any more question from the participants? Okay, so if there is no other participant, we would like to thank the speaker for your wonderful talk and giving your time for this particular event. And if there is any other question, we can probably drop a mail or something like that for further kind of thing participants. So
sure.
It was very nice having you, Dr. Solario, for this talk and wonderful talk. We enjoyed you having today.
Thank you for inviting me. Have a good evening, everyone.
Okay. Okay.
Bye-bye.
Bye. Okay, so we have our next speaker is ready. Oh, Pinaki, are you there?
Yes, I'm here. Am I audible?
Yes, but shall we have some 5 minutes break or so? Then because our schedule says that it is from 9 p.m. but since the previous speaker is over, we will probably have 5 or 10 minutes break. Then we will proceed with the next session.
Okay.
Okay. So we'll have just 10 minutes break. Then we will resume the session.
Sure. So 8:45.
Yeah. So we will wait for 10 minutes. Then we will resume the session. Okay.
Okay. Thank you.